So Pythagorean theorem story problems. So we're going to start by talking about the fact that we have to draw pictures for every single one of these in order to solve them, because otherwise you won't know what parts of the triangle that you have. So we're just going to read through the story problems. We'll read through them more than once. We're going to underline important information, draw the picture, and just make sure that we're doing this correctly. So it says the slide at the playground has a height of 6 feet. The base of the slide measured on the ground is 8 feet. What is the length of the sliding board? So let's read it again. The slide at the playground has a height of 6 feet. So let's draw the slide. Whoop. And we got to have the ground. And then up this side we can imagine is the ladder. If you want to like actually make it look like a ladder, if that helps you, you can do that. Okay, so we drew the slide and we're hoping that this ladder makes a right angle with the ground. So this is where our right angle should be. Now when it says the slide at the playground has a height of 6 feet, where is that 6 feet going to go?
That side.
Which side? This or this? This. Okay, so the 6 feet, the height is actually where your ladder is. That's how high it is above the ground. Whenever they give you a height above the ground, height of 6 feet, that always means the straight up height, okay? Then it says the base of the slide measured on the ground is 8 feet. So on the ground is a good clue that we're going to put that 8 feet on the ground. So you want to look for those words that tell you where these are going to go. And then the question says, what is the length of the sliding board? Sliding board is just a fancy way of saying the slide itself. It wants to know how long the actual slide is. So that's going to be our variable. So I'm just going to call that x. All right, so like I said, we hope that this ladder and the ground make a right angle. It should. The ladder should be straight up and down. And so this is a right triangle. And when we have right triangles, we can use the Pythagorean theorem that we've been talking about. A squared plus b squared equals c squared. And A and B are always the legs. And the legs are always the two sides that make the right angle. So this is going to be A and B. Or you could do A and B. It doesn't matter as long as 6 and 8 both go on this side of the equals. So we could set up 6 squared plus 8 squared. And then you could keep this c squared, or we could put x in and call it x squared. It doesn't really matter what we call that side. Do you guys like c or x?
X.
X works. It doesn't matter. It's the same thing. And then we'll fill in the information. So remember our order of operations, we have to do the powers first. So 6 squared means 6 times 6, which is 36. 8 squared is 8 times 8, which is 64. And I'll just copy down the other side of the equation. And then if I add 36 and 64 together, I get 100 equals x squared. Now, a mistake that a lot of us make, and this is just every time I teach this, is people will get down here and think that they're done. Well, I guarantee that slide is not 100 feet long. That would be a very big slide, especially if it's only 6 feet off the ground. It would just, you probably wouldn't go anywhere if it was 100 feet long. So what do I still need to do to this?
Square.
Okay, it's squared already. We want to do the opposite, which is square root it. Okay? So if we square root both sides, the square root is the opposite of a square, and that just gives us x. And if we square root 100 on our calculators, we get 10. Now in our final answer, we should label this. This was 6 feet and 8 feet, which means that this is 10 feet. And so that's the length of the sliding board would be 10 feet. If you want to write that on here, sometimes writing your answer back on the picture will help you figure out if it makes sense. If I had stopped at 100 and put 100 here, automatically I'd be going 100 feet's way too long. There's no way. that you'd have 100 rulers for the length of your slide. Just nobody makes slides that long. And so then I would know that I'd forgot to do something.
It wouldn't be able to fit anyway, so if it's 6 and 8.
Yeah, if it's 6 and 8, then it has to be 10 in order to fit. And that's why the Pythagorean theorem is so cool. Because this is the only number that fits with both of those and makes a right angle. Okay, so let's go down to number 2. All right, so the bottom of a 13-foot straight ladder is set into the ground 5 feet away from a wall. When the top of the ladder is leaned against the wall, what is the distance above the ground it will reach? Okay, so we kind of have an idea, but let's go back and read it again before we draw our picture. The bottom of a 13-foot straight ladder is set into the ground 5 feet away from a wall. Okay, so we need to have a wall. If you want to label that wall, just to remember what it is, you can. And we're going to have the ground. And then we're going to have a ladder leaning against the wall. And this should be a right angle. Hopefully your wall and the ground make a right angle. So here's your ladder. If you want to make it look like a ladder, kind of. I'm not very good at drawing, but sometimes that helps me remember what's what. So that's the wall, that's the ground. There's my ladder. And labeling this can kind of help you figure out where your numbers should go. So it says it's a 13-foot straight ladder. Well, since I have this labeled, that makes it really easy to put that 13 feet here. So that would actually be the hypotenuse this time for this right triangle, because it's across from the right angle, and that's going to be our longest side. And it's set into the ground 5 feet away from the wall. Because you know that they're talking about the ground 5 feet from a wall, I can put 5 feet down here on the ground. It's telling you basically the ladder is set into the ground 5 feet from the wall. So here's where the ladder is set into the ground 5 feet from the wall. So if you read very carefully, it tells you exactly where to put all of the numbers. And then it says, when the top of the ladder is leaned against the wall, what is the distance above the ground it will reach? So it's wanting to know what is the distance above the ground it will reach. So the wall is right here. We're looking for where the top of the ladder, we want to know how high it is above the ground. And so this side right here is going to be my unknown. We can call it X or just whatever you want to call it. So again, we have a right triangle. We can use the Pythagorean theorem, a squared plus b squared equals c squared. Now, we need to be careful because we just said that this 13 feet is the hypotenuse, which means that this side is c. That means that on this side, I have to have 13 squared. If they give me the hypotenuse, I try to put that in first so that I don't mess it up. And then I have x, and then I have 5, and that's my a and b sides. So we'd have x squared plus 5 squared. So we just want to be very careful that the two legs of the triangle, the two sides that make the right angle, are going on this side, and the hypotenuse, which is that longest side that's across in the right angle, has to go on this side. If you get that set up correctly, I think you guys will be good because you're pretty good at solving these, but sometimes we get this mixed up where everything needs to go. Okay, so the next thing we're going to do is our powers. So x squared, we don't really know what x is, so we're just going to leave that x squared. 5 squared we can do. That means 5 times 5, which is 25. Good job. And then 13 squared, you might not know. It's on our poster on the wall. It's 169. Now this one is different because the 25 is on this side of the equal sign, and the 169 is on this side. So what do we do? Yes, Ian.
Change 25 to negative 25.
Awesome. So yes, we're going to use negative 25 or minus 25 because we're trying to get the x squared by itself, and that cancels this out. We just have x squared left on the left side, and then we have 144 on the right side. And like I said on the last problem, this is where a lot of people will just stop and go, oh, it's 144 feet above the ground. It's not if a 13-foot ladder is actually reaching. So what do we still need to do? Square root. Good job. So we're going to square root the x squared and square root the 144. And if we square root 144, we get 12. And I'm going to label that with feet because everything in the problem is in feet. And so that means that this ladder was 12 feet above the ground here. So the ladder is only a little bit longer than this height. I probably drew this a little too far out when I drew it, but that's okay. All right, so our main steps are to read the story problem through several times, draw a really good picture and label everything, just make sure we understand where all the numbers and go and what part we're looking for, and then we have to correctly put it into our formula and solve. Okay, so let's look at the next problem. It says, in shop class, we don't have shop class. That's a class where you would make stuff out of wood or sometimes out of metal. Leather. I know. We had a lot of stuff when I was in middle school. I wish you guys had shop because we had so much fun. So in shop class, you make a table. So pretend in your mind you made a table. The sides of the table measure 36 inches and 18 inches. You guys know the little tick marks mean inches. If not, we'll label that on here off the screen. So inches. So these little, if you have the two little marks, that means inches. If the diagonal of the table measures 43 inches, is the table square? And they're going to explain what that means. In construction, the term square just means the table has right angles at the corners. So this seems very confusing, but we're just going to try to draw it. So we're going to draw the top of the table. And if you wanted to make it look like we're looking at an angle and put some table legs on there, you certainly can. I'm not very good at drawing, but you can kind of tell. So we're looking at the tabletop. Okay, it says the sides of the table measure 36 inches and 18 inches. So on the long side, I'm going to put 36 inches. And on the short side, I'm going to put 18 inches. So evidently this is not a dining room table. This is probably like a table you'd put against the wall in your living room. Yeah. It's not that big. And then it says the diagonal of the table measures 43. What is a diagonal? Yeah, from corner to corner. So I'm going to draw it this way. So my diagonal is 43 inches. And we want to know if the table is square, which means they want to know if it has right angles. So we're trying to figure out, I'm going to put a question mark right here, we're trying to figure out if that is a right angle. And if you look, when we drew the diagonal, we just made a triangle out of the rectangle. We made it into two triangles. And so really what it's asking is it a right triangle? And in our last lesson, we saw that we can use the Pythagorean theorem to figure out if this is a right triangle and if this is actually a right angle. Middle school shop class is the first time I ever saw the Pythagorean theorem. Our shop teacher told it to us so that we could tell if things were actually square, if it had right angles in the corners, if we cut things correctly. So just a little tidbit. It's very useful even outside of math class. So if we're using a squared plus b squared equals c squared, and we're trying to test if this is a right triangle, which one of these goes in for C?
43.
The 43, because that's the longest side. The hypotenuse, if it's a hypotenuse, goes on the longest side. And then the other two sides would go in for A and B. So 18 squared and 36 squared. So we have to think about that. The longest side has to be over here. And then we're just going to check and see if it works out. So if you do 18 squared on your calculator, you get 324. And 36 squared is 1296. 1,296 is how I should read that. And then 43 squared is 1,849. And we're going to see if these add up. So I'm using my calculator in the background. Actually, I'm looking at my notes from last year, but I did all this with the calculator. I did not know what 36 squared and 43 squared in my head. Just used my calculator. And then I'm going to add these two up.
You can already tell they're doing that.
Yeah, this is 1620, and this is 1849. So I could put little not equal signs on these. It did not come out equal. This side is less than, which tells me that it is an obtuse triangle, which they didn't really need to know that much, but they wanted to basically know if we have a right angle in the corner. So we're going to say no, the table is not square. That always confused me because obviously this table is not a square, but when you're building things, they will use that term square to just mean that it has right angles in the corners. And it's not off by a lot. It probably looks close to a right angle, but just a little bit off. This angle is actually a little bit bigger than 90 degrees, which for a tabletop wouldn't be the end of the world. But if you were constructing a house and these were your supports going up and across and they weren't square, things can actually fall down. So this is something that we do use in construction a lot. Like I said, I learned about it in middle school shop class my 8th grade year. I still remember that moment because it was a big math moment for me. Because we had to use it, and he made us check all of our stuff that we built to make sure that we had those 90-degree angles. So it's pretty useful. All right, let's take a look at the next side, the second half of our lesson. It says, in the Old West, settlers made tents out of a piece of cloth thrown over a clothesline and then secured to the ground with stakes, forming an isosceles triangle. How long would the cloth have to be so that the opening of the tent was 6 feet high and 8 feet wide? So this one we definitely need a picture to sort of visualize. So let's just start at the beginning. In the Old West, settlers made tents out of a piece of cloth thrown over a clothesline and secured it to the ground with stakes, forming an isosceles triangle. So imagine here's my clothesline, okay? And we're going to throw basically a big tarp over it. So I'm going to try to draw this. I've practiced. Here is one side of the tarp, and then you can kind of see.
Well, I made one of these at Shayla's house.
You can kind of see, like back there, if you just want to lightly draw that in. And when it's talking about an isosceles triangle, it's talking about this part. I'm going to highlight that with a color just so you can see it. So they're talking about this opening right here as being an isosceles triangle. Now that's bringing up some vocabulary we haven't seen for a while. That just means that this side and this side are the same, because there's going to be the same distance from the clothesline to the ground on this side as there is on this side, okay? And then it says, how long would the cloth have to be so that the opening of the tent was 6 feet high and 8 feet wide? So this is the opening of the tent right here, what I just highlighted in red. And so we want it to be 8 feet wide. And then when it says 6 feet high, that means going right up through the middle. This distance right here, which would make a right angle, is going to be 6 feet. So when I draw that height in there, I actually just broke that triangle into two smaller right triangles. I just cut it in half. So if it was 8 feet all the way across, and I just cut it in half, what would each of these little distances be right here?
4 feet.
4 feet. So I'm going to write a little 4 feet right there. Now if you need to, if your picture gets kind of messy, you can just take this little right triangle and redraw it to the side. I can't tell you how many times I've done that because I just write so much on my pictures I get confused. So my height I know is 6 feet, and I just split the 8 feet in half and now have 4 feet right there. And if I think about this, if I figure out this distance right here, x, that's half of my fabric. So I actually would have to find this and then make sure that I have both sides. So there's a little extra to this story problem, but if you draw the picture, you can see it's pretty straightforward. It uses the Pythagorean theorem, but it does involve a little bit of drawing and thinking it through. All right, so a squared plus b squared equals c squared is the Pythagorean theorem. So we are looking for this side right here. This is x. So which one of these is side C? Which one is the hypotenuse?
The x.
The x. So I'm going to go ahead and just put x squared. You could actually just call it C if you wanted to, but that's where that goes. And then the two sides that make the right angle are the A and B. So I will have 6 squared plus 4 squared. Okay? So 6 squared is 6 times 6, which is 36. 4 squared is 4 times 4, which is 16. And so we did the powers first, and now we're going to add them. We're using our order of operations. We get 52 equals x squared. So what do I do now?
Square root.
Square root. You guys are so good. You're good with the vocabulary. And if I square root this on my calculator, it does not come out a whole number. So let me show you that.
It's between 7 and 8.
Yep, it is between 7 and 8. Good job. So square root of 52 is about 7.211. We're going to round it off to just 7.2 for what we're doing. So it'll be about 7.2 feet is x. So going back to our picture and thinking about this, that means this distance from the clothesline to the ground is 7.2 feet. But that's only half of my tent. So it'd be 7.2 on this side. I also have 7.2 feet on the back side. So I would have to double that, or you could just take 7.2 plus 7.2. Either way works. So I'm going to end up with 14.4 feet in all. So I know that distance from here to here is how long I need that fabric to be if I want it to be 8 feet wide and 6 feet tall. 6 feet tall would make it so that most people could walk around inside. It's a pretty good sized tent. But in the Old West, if you're traveling around, that was where you lived, so you want it to be big enough that you can move around in there. All right, so that one was a little complicated, but with the picture, not too bad. Let's look at number 5. A baseball diamond is actually a square with sides of 90 feet. If a runner tries to steal second base, how far must the catcher at home plate throw to get the runner out? Given this information, explain why runners more often try to steal second base than third. All right, so let's go back to the beginning. Read it again. A baseball diamond is actually a square with sides of 90 feet. So what we're looking at, we're going to say that this is home plate. And we're going to come up here to first base. And then go over here to second base. I'm not very good at drawing this, but it'll work. Over here to third base, and then back here to home. So this is actually supposed to be a square. I drew it very poorly. But it's actually a square that's been turned on its side. So if it's a square, what that tells us is that each of these is going to make a right angle. For example, this is a right angle right here. So all of these, if it's actually a square, make right angles. So, and it tells us that it's 90 feet between all the bases. So this is 90 feet, this is 90 feet, this is 90 feet, and this is 90 feet. So I'm just kind of getting every bit of information on there. So we know it's a square with sides 90 feet. We kind of set it up. We labeled everything. We have it in our mind. Home, first, second, third. Okay? So if a runner tries to steal second base, so that would be going from first to second, right? How far must the catcher at home plate throw to get the runner out? So the catcher here is throwing to second base. So we're actually trying to figure out this distance. So the runner is just going from here to here, but they're trying to throw the baseball from here to get them out. So everybody, you've all watched a baseball game, right? So you can kind of imagine this in your head. So look what we just did. We just made a right triangle. Which side is X? Is it A, B, or C? C. So the X is the hypotenuse. And both A and B are just going to be 90. So we'll have 90 squared plus 90 squared. All right? So 90 squared, 90 times 90 is 8,100. So I'm going to have that twice. And then we add them together to give us 16,200. And then on our last step, you guys have been really good about this. We square root. And that changes the x squared to just an x. And this one also does not come out to be a whole number. So let me put that on the screen. So we're doing the square root of 16,200. And it comes out 127.279. So if I want to round this to the first decimal place, which is a 2, and the number next door is a 7, do I keep the 2 or do I round it up?
Keep it.
If the next number is a 7?
Oh, round it up.
Round it up. So if this number is 5 or bigger, we round up the 2. So it's going to round up to 127.3 feet. Okay, so 127.3 is this distance. So that answers the first question. That's how far they have to throw the baseball. So I'm going to write that on my picture because I think that'll help me answer the second question. So the first question we had to answer was if they tried to steal second base, how far must the catcher at home throw to get the runner out? So we answered that question. And so it's given this information, explain why runners more often try to steal second base than third. So to steal second base, you'd have to go from here to here, and they're throwing at 127 feet. If you're going to steal third, you're going from second to third. How far is the catcher going to have to throw to third base?
90 feet.
Only 90 feet. So that's why they're going to steal here. There's just a little bit more time to steal this because they have to throw the baseball 127 feet rather than 90. Here, they're going to get the ball there a whole lot faster. So we have to write that out somehow. So the catcher has to throw the ball farther to second base than to third base. I think that's just a good explanation. So that answers the second question where we had to explain. And it's just that they have to throw it 127 feet here, only 90 feet here. They're going to get it there a little faster. You're going to have less of a chance of actually getting that base and more chance of getting out. Didn't know there was math in sports, did you? It's very much calculated.
Math in everything.
There is math in everything. All right, we're going to do one more. Let everybody get all this written down. So on number 6, it says your family wants to purchase a new laptop with a 17-inch wide screen. Since the 17 inches represents the diagonal measurement of the screen, upper corner to lower corner, you want to find out the actual dimensions of the laptop. When you measured the laptop at the store, the height was 10 inches, but you don't remember the width. Calculate and describe how you could figure out the width of the laptop to the nearest 10th inch. Okay, that's very complicated. Let's just go back to the beginning. Your family wants to purchase a new laptop with a 17-inch widescreen. Okay, we know that. The 17 inches represents the diagonal. I don't know if you guys realize this, but when you purchase a TV or a tablet or a laptop or you're getting a screen for a desktop, when you see those measurements, it's always the diagonal. So let's say this is the screen on your laptop. That 17 inches goes this way. When you say you're getting a 17-inch screen, this is the distance that they're measuring. Aha! And because we know that this is a rectangle, we have right angles in all of those corners. You want to find out the actual dimensions of the laptop. Maybe you're trying to figure out if it fits in a certain bag. When you measure the laptops at the laptop store, the height was 10 inches. So I'm going to put 10 inches over here for the height. But you don't remember the width. Calculate and describe how you could figure out the width of the laptop to the nearest 10th inch. To save some time, I'm going to cross off the describe. We're just going to do the calculate part. Okay? So we're going to calculate the width. I didn't mean to cross off the V. We're just going to calculate the width of the laptop, and then we'll talk about it out loud. So we're looking for the width, which would be this right here. And look, we made a little right triangle. So if we're set up a squared plus b squared equals c squared, tell me what this is going to look like. Where do the numbers go? Tell me how to set this up. Yes, Felicity.
10 inches can either go for A or B.
For A or B.
And 17 would go for C.
17 goes for C. Good. So 17 goes over here. I like to put my x's first, so I'm going to put x squared plus 10 squared, but you could totally switch that if you want to. I just like having the x's first. That's how my brain enjoys having that set up. All right, so let's do all those powers. The x squared just stays x squared because we don't know what x is. 10 squared is 10 times 10, so that's 100. And 17 squared is 17 times 17, which is 189. And if you don't know that, you can get that off of your calculator. What do we do now?
289.
Oh, I don't think so.
Yes, it is.
So if this is...
289.
Oh, it's 289. Oh, I'm sorry. I thought you were telling me that was the next step. You're right. I wrote that down incorrectly. So what do we do next? Minus 100. Good. So we're going to take 100 off both sides. That cancels this out. So I have 189 here. I was looking at my notes and I was a step ahead. And so then the x squared comes down. I just have x squared equals 189. Square root both sides. And it'll come out about, it says to do 1/10 of an inch, so we'll round off to the first decimal. It comes out about 13.7 inches. So if I was describing how to set this up, it's what you guys just talked me through. These two sides, we use the Pythagorean theorem. These two sides would be the legs, A and B. This side's the hypotenuse. And then you could go through all your steps, and you could describe squaring the numbers and subtracting the 100. For the sake of time, we're not going to write all of that out, but we have practiced that in the past. You could just write out your steps. For this, I just wanted to set it up and solve.